Hello everyone. So welcome to our video lecture. In our last class, if you remember, we have studied about elements of symmetry, right? About POS, COS, AOS, AOS. How to discuss like whether the compound is having symmetry or not, right? How to check symmetry in various compounds like cumulins, like biphenyls, like simply a carbon having tetrahedral geometry, having different groups like 1, 2, 3 or 4 different groups. Okay, in all these cases we have studied. So students, if I say it was one of the part to check optical activity, means if a compound is optically active, means it is not having any type of symmetry, right? It is not having POS, nor having COS, nor having AAOS, alternating axis of symmetry. But this is one of the way. Now if we say a compound is unsymmetrical, then it will behave as an optically active compound. Okay, so there are various different ways to check whether the compound will be optically active or inactive. So let's see a few important terminologies which is related to check optical activity. Okay. First of all, we'll understand the term chirality. What is chirality? When we say chirality, it is about checking a chiral center. Okay, now what is chiral center? So, chiral center. A chiral center is one where any atom is connected with 4 different atoms or groups having itself tetrahedral geometry. Okay, now what does it mean? Chiral center means a chiral center is one where any atom is connected with. Means we are having an atom. Okay, now that atom is connected with 4 different atoms or groups. Means suppose we have a carbon, it is connected with 4 different groups or atoms, okay, and having itself tetrahedral geometry, and this atom is having tetrahedral geometry. Clear? So let's see an example. If I simply say one carbon having fluorine, chlorine, bromine and iodine. Okay, so students, you can see that this carbon atom is connected with 4 different groups, 4 different atoms here: fluorine, chlorine, bromine and iodine. So it is called as a chiral center. Okay, now if I say how to represent chiral center, so generally a chiral center is represented by this symbol asterisk, like this. Okay, means it is a chiral center. Okay, clear to everyone? Okay, so once let note it down. Okay, chiral centers in various compounds. Okay, so students, let's see chiral centers in various compounds. If I simply say a carbon having hydrogen, deuterium, tritium and any other group like fluorine, suppose if we say, so you can simply say that this carbon atom is having tetrahedral geometry, first part. Second part, this carbon atom is connected with 4 different atoms, so it is a chiral center. Okay, clear? Now second example, methyl, hydrogen, fluorine and deuterium. Now students, see this one, it was simple representation of a tetrahedral molecule, right? But this one, if I say, so in 3 dimension if you observe, then this wedge part is away from the observer, away from the observer, and this methyl part, this is towards the observer, towards the observer. Okay, so this carbon is connected with again 4 different groups, so we can say it as a chiral center. Okay, now one of the question arises, sir, is it all about carbon atom having 4 different groups? No, it's not about that. It's all about an atom having 4 different groups, and that atom must be tetrahedral in geometry. Okay, so let's see another example. Third, so students, see this example. Here if I say this is pH is your benzene, if I say it represented perfectly, it is having this type of geometry, lone pair, okay. Now from this structure, if you observe, you will find that this sulfur atom is having one lone pair, one double bond oxygen, one carbon here this side, and one carbon this side having this benzene phenyl group, right? Now the question arises whether to consider this lone pair as a different group or not. Okay, so yes, we have to consider lone pair as a different entity. Okay, now suppose you are told that an atom having 2 different lone pairs, so that will not be 2 different. Okay, lone pair means lone pair, but if I say there is 1 lone pair and 3 groups, then consider lone pair as a different entity. Okay, so here if I say in this compound, then this sulfur is a chiral center. Okay, now you can see it is not mandatory for a chiral center to have carbon as the main center. So this sulfur having CH3 group this side, double bond O this side, lone pair this side, and group this side, so it is having one chiral center. Now again the term comes, there may be one or there may be more than one chiral centers in a molecule, right? So let's see further. Next examples. Now let's see this one. Nitrogen is having hydrogen, deuterium, tritium and one lone pair. So obviously we can say here that it is also a chiral center. Okay, this nitrogen having 4 different groups. Next. Now if I say this group, then if we say nitrogen is having hydrogen, deuterium, phenyl and this lone pair, now the question arises, it will be considered as a chiral center or not. So here we need to recall the concept of resonance. Okay, let's see this one. This molecule is actually a benzene which is connected with this nitrogen, lone pair, hydrogen and deuterium. Okay, now if we see the concept of resonance, we find it here that it is having lone pair, single bond, double bond type conjugation, right? So if I draw one resonating structure of this compound, resonating structure represented by this type of arrow, now it will possess plus charge, here it will be minus charge, and again these all are same. Now what difference arises due to this resonance? If I see in this particular structure, if I say in this structure, then this nitrogen is having 3 sigma bonds and 1 lone pair. So for 3 sigma bond plus 1 lone pair, we say that it is 3 bond pair plus 1 lone pair, so sp3 hybridization. Okay, but if I consider this structure, then I can easily see it is having no lone pair. It was having 3 bond pair plus 1 lone pair, but here it is having 3 bond pair plus 0 lone pair. Now when I say bond pair, I means 3 sigma, right? Here also 3 sigma. So in this case, if I see the hybridization of this nitrogen, then it is sp2. So it is not tetrahedral now. It is having trigonal planar type geometry. So here it can be said sp3, but here it is sp2. Now what resonance rule says? According to resonance rule, if a lone pair is in conjugation, then consider the hybridization of that atom with respect to the resonating structure. Means here this nitrogen will not be considered as sp3, it will be considered as sp2. So we can say that this lone pair is in resonance. Lone pair is in resonance. So nitrogen atom will not be considered as chiral center here. Okay guys, so you can understand nitrogen atom in this case will not be considered as a chiral center. Clear? Okay, so note it down, this one. Also you can mention here sp2 as per resonance rule. Okay, so I think clear to everyone. Chiral carbon. Now what is chiral carbon? Now everyone must be having some sense. You can think what will be chiral carbon. A chiral center where that center atom is carbon, then we can simply say that is chiral carbon. Means carbon atom connected with 4 different atoms or groups is termed as chiral carbon. Okay, so here you can see a carbon atom which is connected with 4 different groups or atoms. Like again, if I say H, Cl, tritium, and it is iodine. So this carbon is having 4 different atoms. Okay, or if I draw one, this carbon is having CH3, it is having pH, it is having ethyl, and it is having suppose I say propyl group, suppose. Okay, propyl group. So you can see here this carbon atom will be said as chiral carbon. Okay, clear? Okay, so it will be chiral, it will also be chiral. Clear? So you can note it. So there is a difference between chiral center and chiral carbon. Chiral center is for any atom having 4 different groups, sp3, but chiral carbon means carbon atom having 4 different groups or atoms. Now you may also say carbon having H, Me, F, Et. So it is having 2 different atoms and 2 different groups. So both cases are possible, right? Different atoms or groups or both. Okay. Find chiral centers in. So students, I am giving you a few questions. Here you have to find out chiral centers. Okay, that may be chiral carbon or any atom having 4 different groups. So just check it out. You have to first write down the questions and find out the answers. Then you will check my answers. Okay, so first question. Okay, so find out the number of chiral centers in this. Number of chiral centers here, I mean there may be 1 or 2 chiral centers. Okay, so find it out first. Okay, so let's check. See, in this structure, if I say its IUPAC name is 1,2-dimethyl cyclohexane. Okay, so in this 1,2-dimethyl cyclohexane, this, let's see one by one. This carbon atom, let me draw here properly. This carbon atom is having 1 hydrogen, 1 methyl, this side also methyl. Okay, now check this carbon atom. Obviously this carbon is CH2, 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 CH2. So when carbon is already having 2 same groups, so it must not be chiral center. Okay, so let's come to this one. So here it is having 1 methyl, different, 1 hydrogen, different. Now this side is CH2 and this side is CH. Why? Because this carbon is also having H and methyl. So students, you have to remember that in cyclic compounds also you can check chiral center with this logic. If you move all the 4 sides and you find the different groups, then that center will be considered as chiral center. Okay, so here you can see this carbon is having methyl, hydrogen, this side it is CH2 and this side it is hydrogen and methyl. So this carbon is different and this carbon is different. Even if I say it is 2-degree carbon, because it is connected with this carbon and this carbon is connected with 2 different carbons, so it is 2-degree. And this carbon is connected with this and this, so it is 3-degree. So this carbon is also different. Okay, so in that way this is your chiral center. Okay, now again as it is carbon, so I will say it is a chiral carbon. Now with the same logic I can also say that this one, see, similar to this one, it is also chiral carbon, chiral center. So here I can see number of chiral carbon equals to 2. It is number of chiral center. Okay, here I can say number of chiral center. Okay, so here it is 2. Now I think everyone must have checked this one. So let's see this one. First of all, come to this one. See, wherever you will find, you can, observation is very important here. Okay, see, if I say this carbon, this carbon, this one, this one, this one, this one, or this one, these all are CH2. So in these cases I need not to check anyone. But if I see this one, so it is having 2-degree carbon here, CH2. If I see here, it is having 3-degree carbon, because this side 1, this side 1 and this side 1. And this is also having 1 hydrogen. Okay, because it is 3 carbon bonded and 1 hydrogen. And this is having 1 this side, which is having methyl. So in such a way I can say that this is a chiral center. Okay, so it is your chiral center. Now let's check this one. If I see this one, so it is CH2, it is again CH2. So let's move further. Okay, you have to move further till you get same or different. You have to check an entire molecule. So if I move from this carbon, it is having 1 hydrogen first of all. Okay, now 1 CH2, 2, 3, fourth one is carbon having methyl. Now it is 1, 2, 3, 4. Here fourth one is normal carbon, not having methyl. So I can say this side is different, this side is different, this hydrogen is different. Again it is 3-degree, so it is also different. So this is also a chiral carbon, chiral center. Okay, second. Now third, this one. If I see simply this one, so it is having hydrogen as well. Okay, now it is having hydrogen, and this is what? This is your methyl. Now this is 3-degree carbon, it is 2-degree carbon. So this one also be your chiral center. So I can say number of chiral center equals to 3. Okay, so if your answer for this question was correct, you can give your comment on the comment section. Okay, so this is your correct answer. Number of chiral center equals to 3 in this one. Now let's see this one. So students, what happens? Here I mentioned about 1,2-dimethyl cyclohexane. Here I am telling about 1,3-dimethyl cyclohexane. Now with this carbon atom, if I see, then this side is your CH2, CH2 common. Again, this is 3 degree, this is 2 degree. So this is having this side different, this side different, this is methyl different, and here also hydrogen atom, so it is different. So this will be considered as a chiral center or chiral carbon here. Okay. Now, if I see this one, again it is having methyl, same to this one, it is also a chiral center. So here I can say number of chiral center equals to 2. Okay. For 1, 2, now here 1, 3 dimethyl. Now let's see about 1, 4 dimethyl cyclohexane, what happens? See, this carbon, these 4 are CH2, need not to think. This is hydrogen, this is methyl. Okay, here also it is methyl and it is your hydrogen. Clear? Now, in this, if I see this carbon, one side methyl, one side hydrogen, that is okay. I move this side or this side, common CH2. Again this side or this side, again common CH2. Now this one, this is common for both. So I cannot say this as a chiral center. Not chiral center. Okay. So this cannot be considered as a chiral center because from this carbon, I cannot get 4 different groups on moving all the sides. Clear to everyone? Now come to this one. Again, same like this. These two are different, but this side or this side are, so it is also not chiral. So number of chiral center here equals to 0. I think everyone must have noted it down and understood this thing, how to check chiral center and chiral carbon. Okay, let's see a few more examples. Find total number of chiral centers in the given compounds. Okay, so students, you have to find out total number of chiral centers. First of all, let's see RCONHMe. Second, okay, so find out number of chiral centers in this one. You have to also check whether it is chiral center or not. Done? Okay. So first of all, this one, I can see here this nitrogen is having hydrogen, methyl, this carbon bond, and here it is lone pair. So it must be chiral center, right? No. Here it is having resonance. Okay. So due to resonance, it is again sp2. So it is not having 4 different groups. So this will not be a chiral center. Okay. And obviously this carbon is not a chiral center. So here number of chiral center equals to 0. Clear? Next to this one. Now this nitrogen is having 4 bonds. So it is sp3. One condition is okay. Tetrahedral. That is okay. But here it is having 2 common atoms hydrogen. So number of chiral center equals to 0. Okay. Now this one. This nitrogen is having lone pair, hydrogen, methyl, ethyl, and this lone pair. So number of chiral center equals to 1. Okay. Clear? Now this one. This nitrogen is having hydrogen, deuterium, tritium, and methyl plus charge. So it is having number of chiral center equals to 1. Why? 4 different groups. Clear? So students, I mentioned you about all cases of chiral centers, especially in case of nitrogen, as well as again if I say one case of see, if I say this example, so this sulfur is having 4 different groups, tetrahedral geometry, but this is 2 same, double bonded oxygen, double bonded oxygen. So at present it is not a chiral center, and this carbon is CH2, so it is not a chiral center. Okay, now what can I do if I say that this oxygen is O16 and it is O18? Now what will you say? If I say this oxygen is oxygen, you know isotopes O16 and O18, just like HDT, O16, O18. Now what will you say? That this sulfur is having one different group this side, one different group this side. This is also different, this is also different. So in this case, this sulfur is a chiral center. So in this way, number of chiral center here equals to 1. I think it is very clear to everyone. Fine. Okay. So let's come to next example. 5th, 6th. Okay, look at these examples. Now here you can see in these three cases, this oxygen is having two lone pair, so this is CH2, so it is not a case. But this one, methyl, hydrogen, oxygen, and here CH2, so here it is a chiral center. Number of chiral center equals to 1. Now in this one, we can say these CH2 and this CH2, no case to think over it. Now this will be 3 degree CH2, 3 degree with methyl, so this is a chiral center. Again this one, CH2, CH2, carbon with methyl, CH2, 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 CH2. Now this is 3 degree in front and hydrogen, so it is a chiral center. Now again, this carbon having methyl as well as it will be having one hydrogen. This is 3 degree, this is 3 degree, but this is methyl, so this is a chiral. Again this is also a chiral center. So I can say here it is number of chiral center equals to 1, 2, 3, 4. Okay guys, so next one. Now this is carbon having hydrogen, methyl, CH2D and CHD2. Now you can think that sir it is having carbon, carbon, carbon and hydrogen, but you have to check the group. Now it is methyl, CH3. It is different because it is CH2D, and it is also different because it is CHD2. So this will be considered as a chiral center. Okay, so number of chiral center equals to 1 here. Now one of the best question arises that for an alkane, how many carbon atoms are needed to generate one chiral center? Okay, minimum number of carbon atoms required in an alkane to form a chiral center. Okay, so let's check. You first solve by yourself. Okay, number of carbon atoms needed by alkane having one chiral center compound. Okay, so I think everyone must have drawn. The simple logic comes is most of the students must have drawn that sir you can say H, D, T and just put it methyl, because I cannot, when it comes to alkane it simply means it must be having carbon hydrogen part, right? So you can say H, D, T and methyl, right? Isn't it? No? Okay, it is not correct. Why? Because when you say alkane, the standard meaning is CnH2n plus 2. Okay, so you cannot mention here isotopes. Isotopes will not be considered in this case. So let's see what can be done. Okay, so what I can do is a carbon having hydrogen, here it is CH3, here it is CH2, CH3 and here it is CH2, CH2 and CH3. So carbon having H, Me, Et, prop, methyl, ethyl and propyl. So here you can see that this carbon atom is having 3 plus 2, 5, 1, 6, 1, 7. 7 carbon atoms needed. Okay, for an alkane having one chiral center, 7 carbon atoms are needed. Clear to everyone? Okay, now I am just changing in this question. I think you first note it down. I am just changing a small thing in this question. Now I want to ask, what about if I say needed by alkene, number of carbon atoms needed by alkene having one chiral center compound, means you have to draw one alkene. It must be having one chiral center. Okay, so again, now isotopes will not work here. Okay, what we can do is, for alkane I know that general formula is CnH2n. Okay, suppose I am having one carbon with hydrogen, means because one carbon having 4 different groups. So let's check that carbon. Suppose if it is having CH3 and this part is having double bonded, because now you can see that this one is your alkene part, CH2, and this is your H. Okay, now this carbon must be having 4 different groups. So H, Me, this ethynyl part, and let's see here as you cannot here use the isotopes, so you can see here ethyl, CH3 CH2. Okay, so this is the best possible answer. If you find the other possible answer, then just write in the comment box or message me. Okay, so in this case it is having 1 2 3 4 5 6. If I ask about the IPSC name of this compound, then you can simply mention it here as 1 2 3 4 5. So it will be 3-methyl pentene. So it is alkene. Okay, so I think everyone has done this part. Now again, if I say about, if I would have asked about alkyne, then you can simply say carbon with H, CH3, C triple bonded H, and this will be your Et. So here you can see that number of carbon atoms will be 2 1 3 1 4 1 5 6. 6 carbon again needed. Okay, so it is clear, for an alkene or alkyne to make a chiral center, with this strategy you have to go. Also, don't use isotopes when it is said alkene or alkyne. Clear? Okay. Now I am telling you one important concept. What is that? Prochiral carbon. Now what is prochiral? It is PRO, prochiral carbon. See, when you say chiral carbon, it simply means carbon atom connected with 4 different atoms or groups. Now what is prochiral? Suppose I say carbon atom is connected with group G1, G2, hydrogen. Okay, now if I see this compound, then carbon is having 2 different groups, G1 and G2, but having 2 same hydrogen atoms. Okay, or suppose any 2 similar groups were connected here. Okay, so such compound is called as, such carbon atom which is connected with 2 different and 2 same groups or atoms is considered as prochiral carbon. How or why? Let's see. Replace hydrogen by deuterium. Now I am replacing hydrogen by deuterium. Now again the question arises, which hydrogen? Because when we see, it is not chiral as such. Right now it is not chiral, but when I replace any of the hydrogen, suppose I say this hydrogen is replaced, which is in dash, so this carbon will be having G1, G2, hydrogen and deuterium, so it will become chiral carbon. Okay, so we can say, what is prochiral carbon? Carbon atom connected with 2 same atoms, groups and 2 different atoms, groups when replaced. See, carbon atom connected with 2 same atoms, groups and 2 different atoms. When replaced common atom or group by some different atom or group, it becomes chiral. Okay, now you can see carbon atom connected with two same atoms or groups, and two different atoms or groups. When replaced common atom or group by some different atom, common atom or group, when replaced common atom means I have to replace only one part, okay, by some different atom or group, it becomes chiral. Let's see, I can say G1 as it is, G2 as it is. Now suppose this is hydrogen as it is and it is replaced by D, then chiral carbon is generated. So this is called as pro-chiral carbon atom. Okay, clear to everyone? Now one more concept lies here. Suppose two atoms were connected in this way, so you have both possibilities, you can replace this one or this one. So in that way, two possible cases, G1, G2, D here and H here. Okay, so these two must be having two different conformations, we can say, means arrangement in space is different, right? If you say this G1 and G2 in the plane of this board, you can say with carbon, hydrogen is towards you and deuterium is backside. Now in this one, G1 and G2 as it is, but deuterium is towards you. Okay, so these two are different cases. Is it clear to everyone? Pro-chiral carbon. Okay, so students, you have understood about chiral center, chirality and chiral carbon as well as pro-chiral carbon. Okay, simple in pro-chiral what we said, when there is sp3 hybridized carbon atom and one of the group is replaced, one of the atom or group is replaced by another atom or group such that the carbon becomes chiral, then such carbon will be pro-chiral. Now let's see a few different cases. Now see, this is a Fisher projection. Okay, now I just mentioned you in tetrahedral geometry, but see, in this optical isomerism part we will be studying and we will be dealing with such a different projections having chiral centers. In this question you can see here it is Fisher projection. So this chiral carbon, because H, D, T and Br, so this is your chiral carbon. Okay, number of chiral center equals to 1. Now what happens? This one, if I see this Fisher projection, here also I can see that this carbon is having chlorine, hydrogen, COH, and this is entire different part with respect to this one. So it is a chiral center. Again this one having hydrogen, bromine, COH, and this entire part is different. So this is also chiral center. So number of chiral center equals to 2 here. Okay. Now what happens if I say this one? So if you remember this one, then this compound is called as tartaric acid. Okay, tartaric acid. Now in this case we can observe that this carbon is having hydrogen, OH, COH, and this entire portion is different. So it is a chiral center. Again same this one, OH, H, COH, and this part, it is also a chiral center. Okay, now here comes a thought how to represent this in Fisher projection. COH, COH, let's keep vertical line with carbon atoms. Now H, H, OH, OH. In 3 dimension there is one possibility like this. In that case this one, COH, OH, H, COH, OH, H and H, this particular group. So it is a chiral center, and again this one is also chiral center. So you are having 2 chiral centers. Now there is one more possibility. As we are studying stereoisomerism, means spatial arrangement in space is different. So the other structure possible can be COH. Now you can see this one as OHH, keeping this part same, but this part changed, H and OH, COH. Now students, in this case also you will say the same thing, that sir, it is having this part as chiral center and this part as chiral center. So what difference lies here? What is the basic difference in these two cases? Okay, so let's understand it logically. When I say a compound is optically inactive, means it is symmetrical. Okay, so there is no need of discussion about it. But when I say it is optically active, so we studied about symmetry, it must not be having any sort of symmetry, right? Now let's understand what I discussed. I discussed about chiral center, atom having sp3 hybridization and all four parts are different. So in that case, from that chiral center, if you cut, then you cannot find mirror image of each other. Okay, when you have a chiral center, one chiral center in the molecule having all the four groups are different. So if you select any plane, no POS, no COS, no AOS. Okay, so that is the best way. If compound is having chiral centers, first check it and then check POS, COS and all. Now let's see this example. This example, I can say this one is having plane of symmetry, right? See, in spite of having two chiral centers, it is having plane of symmetry, so the molecule is symmetrical and it is optically inactive. Okay, but if I see this one, as we have discussed such example, it is not having COS, not having POS, POS, COS absent, but number of chiral center equals to 2 in both the cases, right? So students, remember this point. It is not mandatory for a compound that it must be having chiral center 1, 2 or 0 or so on to be optically active. And also, if compound is having chiral center, you cannot say that it must be optically active. It may or may not be active depending upon symmetry. But for single chiral center compound, we can ensure that if it is having only one chiral center, then it must be having optical activity. Okay, clear from this? Now what happens? Suppose if I say a compound is having one chiral center, it is optically active. So what about its optical isomers? What is that? So students, it is actually the mirror image part of that compound. Okay, let's see it. Suppose one atom fluorine. Okay, now as we see here, it is chiral center and one chiral center, so it is optically active. So how to draw its optical isomers? So students, understand, the mirror image of this compound will not be superimposable to each other. Okay, and such compounds are called enantiomers. Now here comes another term, enantiomers. Okay, enantiomers. Now what will happen? As it is having number of chiral center equals to 1, okay, this compound is optically active, POS absent, COS absent. So when you draw its mirror image, what will happen? This carbon is attached with hydrogen this side and tritium this side. Say in 3 dimension you have to observe. I'll make it. Now this part will be flipped. This F will come this side and this D will come this side. Okay, so here what happens? In 3 dimension, if we will observe that compound which is optically active, we have to draw its mirror image, and that will be a very different compound. Okay, if we see, then both the compounds having different properties in various ways. Okay, but their physical properties will be same. Okay, and such compounds which bear non-superimposable mirror images are called enantiomers. Okay, means if a compound is optically active, so we have to draw its mirror image part, that will also be optically active, but both will be different compounds. And one more thing, they will not be superimposable on each other. Now what is the meaning of superimposable? Means if I put up this compound, if I hold this compound and I keep it here, so it will not superimpose. All atoms will not superimpose on one another. Now if I pick up this atom, this molecule, rotate it and now keep it in this, also it will not superimpose. Okay, so in such case, remember, enantiomer means optically active compounds which have non-superimposable mirror images. Okay guys, so we'll continue this part in our next video lecture, right? We'll start from enantiomers, but till then you think about it, think yourself how that one tetrahedral part, you have to imagine in this compound only. I am giving you this task. Understand this carbon having hydrogen, deuterium, tritium and fluorine. Assume yourself, use that 4 pens I used in last lecture. Think yourself, if this carbon is having one hydrogen, deuterium, tritium and one more here, this side fluorine, I will draw mirror image. Okay, I will keep mirror here or mirror here. Any side you can keep the mirror. Mirror image will be there. So if I put, see, this is the main part, this is the mirror image. So if I put this mirror image part here, it will not superimpose. If I rotate it and keep, again it will not superimpose. So you have to do this experiment by yourself at home. We'll continue it next lecture.